All right, you guys. So, here we are. We're back, and we're talking about similarity and volume. Okay, so the big idea, just the one formula, if that's all you take away, is if you have two similar 3D objects, then the ratio of their volumes is the ratio of any corresponding pair of one-dimensional lengths. So, like for example, that could be their heights are corresponding, and so the ratio of their heights to the third power is the ratio of their volumes, okay? And again, this could be any corresponding length. It could be like the circumference of the base, if this is a cone. It could be the slant height. It could be an arbitrary like lightning bolt on the side that got enlarged. So any single corresponding one-dimensional length to the third power, that's the ratio of the volumes of similar figures. Okay, so the y here is the same as y, the ratio of the areas, is to the second power. Right, so every 3D volume is really, when you break it down, a product of three orthogonal measurements, okay? Now, orthogonal just means perpendicular, but more than one dimension, because when you start to say, like, perpendicular to a plane, you can't just say forms a right angle, because, like, it could form a right angle this way, but that still leaves a degree of freedom that it could tilt to either side while still forming a 90-degree angle. That way, maybe this way is like 180, 170, 100, whatever degrees. So orthogonal just means in more than two dimensions. Anyways, so 3D volume, product of three essentially perpendicular measurements. So for example, in a rectangular solid here, the volume's length times width times height. When you're looking at a pyramid or cone, it's the area of the base times the height, and the area of the base is always two measurements here, so length times width, or if it was a circle, it'd be pi r squared, where each r, those two are perpendicular, and then you have times the height. So there's 1, 2, 3, 1, 2, 3. Well, if these shapes are similar, that means every one-dimensional length gets enlarged by a scale factor. So what happens in the equation is the length gets a k, the width gets a k, the h gets k. So all three dimensions get multiplied by this scale factor, right? Whether it's bigger or smaller. So whether it's growing or shrinking, it gets multiplied by the scale factor. Same thing over here with the volume of a pyramid. All three one-dimensional lengths that were used to calculate this volume get enlarged by that scale factor, and we can just factor that out, right? So for this, it's length times k, width times k, height times k. We take those k's all out, and we get that exact same volume. Whoops, that was supposed to be a square. We get that exact same volume times that scale factor to the third power. And it's because all three dimensions got enlarged. So there's three copies of k. So that's why we get the k to the third power. Okay. So just overall, like looking back, what we have is if we have two similar figures and we have any pair of corresponding lengths, right? Again, that could be matching perimeters, matching heights, matching bases, matching a side length, any corresponding length, and we get the ratio is A to B. Well, then we know the ratio of every one-dimensional length is A to B. So that could be, again, height, perimeter, radius, any one-dimensional length. Every two-dimensional measurement, aka an area, is a squared to b squared. I don't know why I put a slash through that. And that would be like area. That's also surface area. So surface area is on a 3D shape, but it's still a 2D measurement, right? You're saying what 2D amount of area will cover this 3D shape. And that can be bent and warped, right, into a third dimension, but it's still a two-dimensional quantity. Right? You're still calculating it by saying one length times a perpendicular length. So it's got two copies of the scale factor. So again, if the ratio of corresponding one-dimensional lengths is A to B, then every one-dimensional length is A to B. Every two-dimensional thing, area, is A squared to B squared. And every three-dimensional, aka volume, is A cubed to B cubed. Some little extensions for volume. Is it might be like more real world, like, oh, you have water or sand filling a container. That's volume. Or it might even be like, what's the weight of an object? You'll see that in some problems. And as long as it's made of the same material, like for example, it's a uniformly dense steel ball, then adding more volume just increases the weight. And it's because the mass or the weight is equal to simply just the density times the volume. And so if you up one, it ups the other in a linear fashion. And so the formula still works to calculate the ratio of the weights. It's the same ratio as the volumes. Okay, let's do some problems now. All right, so it says these pyramids are similar. And beyond that they're similar, it also says that the ratio of H to capital H is 4 to 7. So, oh look, that's the height of this pyramid. The height of this pyramid, those are corresponding one-dimensional lengths. So we know that we start with a 4 to 7 for the ratio of sides or the ratio of one dimension. So that means all areas would be 4 squared to 7 squared, and all volumes would be 4 to the third, 7 to the third, right? And so this is all the 2D, this is all the 3D. Let's see what it's asking for. It's asking for the volume of the large pyramid when the small is 320. So what we get is 4 to the third to 7 to the third, the ratio of their volumes, is equal to the small one, 320, to some large volume. And so now all we need to do is solve this. So I'm going to cross multiply. I get 4 to the third V equals 320 times 7 to the third. And then I just divide both sides by 4 to the third. And so we get the volume is, and whatever this comes out to be, 320 times 7 to the third power, all over 4 to the third power. And some 4s will cancel out with 320s. I'll leave the simplifying the arithmetic to you guys. Okay, so next problem. The ratio of the lengths of corresponding edges of two similar triangular prisms. So we've got two similar triangular prisms here. And that one's similar to, I don't know, a bigger one here. Okay, whoops, that was a solid edge. And let's just pick any edge, right? It just says corresponding edges. So I don't know, let's say this top edge here and this top edge here. The ratio is 5 to 3 from the bigger to the smaller, okay? So what that means is all of our 1D stuff is in ratio 5 to 3. All of our 2D stuff, whoa, that's not a 2D, is 5 squared to 3 squared. And all 3D stuff is in a ratio of 5 to the third, 3 to the third. Okay, so let's see what it's asking. What's the ratio of their volumes? Oh, the ratio of their volumes is 5 to the third, that's 125, over 3 to the third, that's 27. And it can't be simplified because that's made of 3 primes and that's made of 3 different primes, right? Okay, 6 says the ratio of volumes of two similar pentagonal prisms. So pentagonal prism, right, is a pentagon and then dragged through space and time into the back there. Okay, so we've got the ratio of the 3D volumes is 125 to 8. I don't know why I put the 125 on top. Let's put the 8 on top. So that's the way they gave it to us. And then we want to know the maybe 2D. We also maybe want to know the 1D. And so this one here is the A to the third, B to the third ratio. And so if we take the cube root of this really quick, we could find that that is equal to, so the cube root is what number to the third power equals that. You can punch that into a calculator as using the X to the Y button, and you could raise 8 over 125 to the 1/3 power. That's how you could do the third root. Anyways, the third root of this would be 2/5 because 8 over 25 is the same as 2 to the third power, 5 to the third power. So that means the 2D areas here would be 2 squared, 5 squared, or 4 to 25. And the 1D ratio would just be the 2 to 5. So this is 2 to 5 in one dimension. This is 2 squared to 5 squared in 2 dimensions. And then 2 to the third, 5 to the third in 3 dimensions. Or another way to just simply start with the ratio of the volumes and get to the ratio of any one-dimensional length. Here they said heights. Doesn't matter if they would have said ratio of a perimeter, a length, a height, a side, an edge, right? Whatever they're going to say that's one-dimensional length, all you need to do to get from the volume over is say start with that 8 over 125 and take the third root, because you know this is the 1 to the third power and you want the 1 to the 1 power. And so you just need to take the third root. All right. Sorry. The ratio of weights of two spherical balls is 8 to 27. Now, as long as these are uniformly dense, right? And it just says steel ball. So let's say this is a perfectly made steel with no imperfections. So it's got this uniform density, right? So the mass or weight of that is simply equal to the density of it times the volume. And so this is the density of it. If that's just a constant, like say 3, so then it's just 3 times volume. So whatever the volume, the ratio of the volumes is, right? Then we just have 3v1 to 3v2 is the ratio of like weight 1 to weight 2, where this is just the density, and the density on top and bottom of those two weights would cancel out, and that would give you that the ratio of their weights is the same as the ratio of their volumes. So when it's saying what's the ratio of their weights, really what it's saying is what's the ratio of their volumes, given the fact that they're uniformly dense. So it's not like oh, I'm going to slap some light material on the outside, and so now the inside is denser, heavier than the outside, lighter layer. That would be a more complex question. But here we're growing the exact same thing, steel, and just adding more of the exact same thing, steel, and so the ratio of their weights is the ratio of the volumes. Okay, so what's the ratio of their diameter? So again, we're going from a 3D volume weight to a 1D length diameter. So all we need to do is start with our 8 over 27, which we know is our 3D a cubed b cubed, and we want to go to, we want to go to a over b, and so what we do is we go to the cube root of 8 over 27, and so a over b is 2/3, okay, because 8 is 2 to the third, and 27 is 3 to the third. So that was our a over b. So if the ratio of their volume, if the ratio of their weights is 8 to 27, that means the ratio of their volumes is 8 to 27, and then cube rooting that means the ratio of their diameters is 2 to 3. A sculptor creates a bronze statue that weighs 38 pounds. Again, this is a bronze statue, so it's all one material. That's all uniformly dense. She plans to use a version that will be 4 times as large in each dimension. So in other words, the A to B, the one-dimensional ratio, is 4 to 1. Okay, so then that means the 3D ratio, which is, and again, this is either volume or weight if it's a uniformly dense thing. This is all made of bronze, is A to the third, B to the third. So in other words, it's 4 to the third over 1 to the third, or 64 to 1. Okay, so 4 times as large. How much will the larger statue weigh? So we have small to large, and we go, all right, so we know that it's a 64 to 1 ratio is equal to the actual weights is 38 pounds for the smaller, and we're looking for the big weight, and so we just cross multiply, and that's, that's 1 weight equals 64 times 38, and so the weight of the larger statue is 64 times that original weight of 38 pounds, whatever that comes out to be. Okay, that was it, you guys. I hope you enjoyed the video.